This is example 9-4, blowing on a straw. So we can see this person has a straw in their mouth and they're blowing air through it. Of course, if there's a fluid going through a pipe, right, it will create shear stresses along the pipe walls. So that means there's going to be an overall force trying to move the straw out of this person's mouth. So we are supposed to figure out how much force this person will have to put on this straw to keep it in their mouth, right? So we can think about this force, right? We know that it's due to shear stress, right? So we can say force created by air flowing through straw. All right, we know that if we call that maybe F for Fs for shear force, right, we can say that's our shear stress that we have times the area of the inside of the pipe, of the, not the pipe, the straw. Right, so that'd be pi times d, which is the diameter of the pipe, of the straw, times its length, L. All right, so that would be our force that we have to find. Now, if we want to use our equations, we first have to check if they're valid. So we need to check if the flow is laminar. So let's say check if laminar, right? So that's our Reynolds equation, RE is equal to rho times V times D divided by mu. In our case, we're given the velocity. We can look up the density of air at 20 degrees C. So that'd be 1.202 kilogram per cubic meters times 3 meters per second. And then we have a diameter of 3 millimeters, so 0.003 meters. And all of that divided by mu, which again we'd have to look up, 18.1 times 10 to the minus 6 Newton seconds per meter squared. And we plug that in, we get 597.7, which is quite a bit less than 2,300. So we have laminar flow, which is good because that means we can use the equations that we have. All right, so we can find out what the shear stress is. Right, if we use our equations, we have our shear stress equation for a horizontal pipe. Right, we have tau of the radius centered in the center of the pipe is equal to R over 2 times delta P over L. All right, so in our case, we want to have it at the wall of the straw, right? So we'd have to do pi of R, right? It's half of our diameter. So that's then just R over 2 times delta P over L. Now we're given the diameter, so we can say the radius is half the diameter, so we can say that would be D divided by 4 times delta P over L. All right. Now, what are we trying to find? We need to find our delta P over L. We're given the diameter, but not the pressure change. So we can solve this for the pressure change. Or we can, much better, we need to find the pressure change from somewhere else. So let's do that. The average velocity in horizontal pipe horizontal pipe with laminar flow. Right, that's another equation that we know, but we also know what the value is. Right? We're given that that value is 3 meters per second. Yeah, 3 meters per second. But we also know what the equation is, so we can take that and solve it for our dP over L. So we can say V is equal to d squared over 32 mu times delta P over L. So we can solve that for delta P over L is then just 32 mu times V divided by d squared. All right, so we can take that and plug that into our tau equation. All right, so we can say we had tau was equal to d over 4 times delta P over L. Just found what delta P over L is, right? So we'd have d over 4 times 32 mu times V over d squared. And so we get some simplifications here, right? We get 32 divided by 4, that is 8. And the d cancels down there, right? So we have 32 times mu times V divided by d. And that's our tau. Now we can take our tau and stick that back into our equation. All right, we said our tau was going to be, or our Fs was going to be tau times pi times d times L. So in our case, that is then tau we just calculated, so 8 times mu times V over d times pi dl. That means the diameters cancel out, interestingly enough. All right, so we get 8 mu V times pi times L. And then we can grab our numbers and plug them in. All right, so we're given that it's at 20 degrees C, so we can look up what the density and the viscosity are. So we'd have 8 times 18.1 times 10 to the minus 6 Newton seconds per meter squared times the velocity, which was 3 meters per second, times pi, and the length of the straw was 225 millimeters, so 0.225 meters. Plug those numbers in, get a force of 3.0706 times 10 to the minus 4 Newton. So a very small number, which makes sense because we blow through a straw. We don't really have to push that hard on the straw to keep it in our mouth. All right, so here is example 9.4, where we figured out what the force was that we have to hold on to the straw if we're blowing on it.